So this video will go over section 2.3 on isotopes. Isotopes, their atomic number, the mass number, and the atomic mass. So what are isotopes? Isotope, the word, is made of the prefix iso, and iso in Greek means same, and top comes from topos, which in Greek means place, same place. So isotopes occupy the same place in the periodic table. And so for an element can have several isotopes, and they will all be represented by the same element on the periodic table, so in the same place. And what distinguishes the isotopes of an element is that they have a different number of neutrons. Remember how an element has a symbol and an atomic number, and the atomic number is also the identity of that element. It's the number of protons, and that cannot be changed. For example, chlorine, here, atomic number 17, has 17 protons, and all the isotopes of chlorines will also have 17 protons. What makes them different is the number of neutrons that they have in their nucleus. And so to represent isotopes, we use the mass number. The mass number is an integer or a whole number that comes from counting the number of protons plus the number of neutrons that are in the nucleus of an isotope. So because it's by counting protons and neutrons, it's a whole number. It's not a number with decimals. And so isotopes are represented with this kind of notation where you have the element symbol, like here we have chlorine. And then to the upper left corner, we will write the mass number for that isotope. And so that will be chlorine 35. So another way to call that isotope would be writing chlorine-35. So to go back to this notation of the isotope. So chlorine 35 in the upper left corner and 17 in the lower left corner. 17 is the atomic number for chlorine. So it could be omitted because it's redundant with the symbol of the element, right? Because chlorine, when you look at the periodic table, you know its atomic number 17. So the information is given already by the symbol. But often it's repeated here. Chlorine 35 would be written like this. And so to obtain the number of neutrons from this, you will take the number of protons. So we know it's 17 from the atomic number. And the number of electrons, because it's a neutral isotope here, so it's also 17. Remember how protons are positively charged, electrons are negatively charged, and if we have as many of protons as we have electrons, then the isotope will be neutral. And so to get the number of neutrons, you do the mass number minus the atomic number, and you get the number of neutrons. That's because the mass number, by definition, is the number of protons plus the number of neutrons. So if you subtract the number of protons, you get the number of neutrons. And so this chlorine 35 isotope has 18 electrons in its nucleus. Chlorine is also found as the isotope 37, so chlorine-37. And the way to represent it would be with this chlorine symbol, 37 on the upper left corner, 17 on the lower left corner. The number of proton is the same because it's chlorine. Number of electron is the same because it's neutral. And the number of neutrons is 37 minus 17 equals 20. So the chlorine 37 isotope has 20 neutrons in its nucleus. So that's the only difference between these two chlorine isotopes. One has 18 neutrons, the other has 20 neutrons. So let's do a learning check. Here you have 3 symbols of carbon isotopes. Carbon has 3 naturally occurring isotopes, carbon 12, carbon 13, and carbon 14. So find the number of neutrons, protons, and electrons in each of these isotopes, assuming that they are all neutral. Again, pause the video to work this out before watching the answer. Oops. Let's go over the answer there. Carbon 12, the first one to the left, has 6 protons because, as the isotope symbol says in the lower left corner, the atomic number is 6. You can look at the periodic table and confirm that. So 6 protons, it's neutral, so it has 6 electrons. And to obtain the number of neutrons, you do 12 minus 6, and it's also 6 neutrons. Carbon 13 in the middle, still 6 protons because it's carbon, atomic number 6. 6 electrons because it's neutral. And to obtain the number of neutrons, you do 13 minus 6 equals 7 neutrons. And carbon 14, still 6 protons, 6 electrons, and you do 14 minus 6 to obtain 8 neutrons for carbon 14. Let's try that with different isotopes. Again, determine the number of protons, neutrons, and electrons in each of these isotopes. Pause the video to work this on your own before you watch the answer. So here, oxygen 16, 8. So oxygen atomic number is 8 according to the periodic table and according to the lower left number there. So that's going to be the number of protons and the number of electrons since it is neutral. To obtain the number of neutrons, you do 16 minus 8, which is 8. So, 8 protons, 8 neutrons, and 8 electrons for oxygen. Phosphorus 31, atomic number of 15. So 15 protons and 15 electrons to make it neutral. And then you do 31 minus 15 to obtain 16 neutrons. Zinc 65. Zinc, atomic number 30. You can check that with the periodic table. So that means it has 30 protons, 30 electrons to make it neutral, and you do 65 minus 30 to obtain 35 neutrons. So here it's the reverse process. From the number of protons, neutrons, and electrons, find the isotope symbol. So you need to write the isotope symbol with the element symbol, and then write the upper left corner, write the mass number, and in the lower left corner, write the atomic number. Pause the video before watching the answer. So when you have 8 protons, you need to look into the periodic table. What is the element that has 8 protons? And we can see that it's oxygen, atomic number 8. So you would write the symbol O, capital O, write the 8 in the lower left corner, and then in the upper right corner, upper left corner, sorry, you would write the mass number, which corresponds to the number of protons plus the number of neutrons. So you add them together, and that's 16. So the first symbol here would be oxygen 16 and 8. So that's the isotope oxygen 16. The number of electrons being the same as the number of protons means that it is neutral, so there's no charge. Now, second isotope here with 17 protons. You look at the periodic table, 17 protons is chlorine. So you would write the symbol Cl. And the 17 on the lower left corner. And then in the upper left corner, you would add the protons and the neutrons to obtain the mass number. 20 plus 17 is 37. So that's chlorine 37. And the last isotope here with 47 protons. 47 is silver. The symbol is Ag. So you would write Ag, 47 in the lower left corner. And then in the upper left corner, you would add 47 protons plus 16 neutrons. And that's 107 for the mass number. So remember, the mass number is the upper number, and it's the sum of the protons and the neutrons. Another learning check. Which of the following pairs are isotopes of the same element? And there is a second question using those same pairs of isotope symbols. In which of the following pairs do both atoms have 8 neutrons? So think about this before watching the answer. And let's go over the first answer. Which of the following pairs are isotopes of the same element? Let me go back here. So same element, because we want the same element and we don't know what is that element. The X here is, it's for you to decide what it is. And so you have to use this time the atomic number that is provided in the lower left corner. And for these two to be the same element, you have to have the same atomic number. Otherwise, it would not be the same number of protons and not the same element. So you want to find the pair that has the same atomic number. And here, solution B would be the answer, because we have both 6 and 6 in the lower left corner. So, and it happens that it would be carbon, right? Atomic number 6 is carbon. So that would be carbon 12 and carbon 14. They both have 6 protons, and the different mass numbers indicate that each species has a different number of neutrons. So these are isotopes. Let's go back to the second question here. In which of the following pairs do both atoms have 8 neutrons? So here you need to do the calculation where you take the upper number minus the lower number, because the upper number is the mass number, minus the atomic number will be equal to the number of neutrons. So solution A would be 15 minus 8, that's 7, and 15 minus 7 is 8, so it's not the same. Solution B, 12 minus 6 would be 6 neutrons, and 14 minus 6 would be 8 neutrons. It's not the same. So the answer maybe is solution C. Let's count the number of neutrons. 15 minus 7 is 8, and 16 minus 8 is also 8. So the answer is C for that question. Both isotopes here have 8 neutrons. And to make sure you are correct, you do the mass number minus the atomic number. So the upper number minus the bottom number, and that gives you the number of neutrons. So isotopes are different by the number of neutrons. And we learned that neutrons are neutral and do not contribute to charges, but they contribute to mass. One neutron is approximately 1 atomic mass unit, just like 1 proton. And so the periodic table lists all these elements, and elements have a number below their symbol, and that number has decimals. And that number with decimals is the atomic weight or the atomic mass of the element. The atomic weight is the weighted average of the masses of the naturally occurring isotopes of a particular element reported in atomic mass unit. And so when you find an element in nature, it's a mixture of the naturally occurring isotopes that that element has. So here carbon, for example, we know carbon has 3 isotopes that are naturally occurring. And when you find a sample of carbon, there is carbon 12, carbon 13, and carbon 14 in it. And so you take the mass of the isotopes and take the weighted average, which means you take into account the proportion of carbon 12 versus carbon 13 versus carbon 14. And you obtain a weighted atomic mass that represents the mass of the element when you find it in nature. And so most elements have 2 or more isotopes that are, naturally occurring and that contribute to the atomic mass of that element. So if we look at the table starting from lithium, we see that lithium has 2 naturally occurring isotopes, lithium-6 and lithium-7. And the atomic mass, the weighted average, is 6.941 atomic mass unit. And so when you look at the weighted average, 6.9 is very close to 7 atomic mass unit, right? And so lithium-7 has an atomic mass close to 7, and lithium-6 has an atomic mass close to 6. Because the atomic mass will come from the protons and the neutrons. And if you count the number of protons and neutrons, you get an idea of about what would be the mass of that isotope. So, but then when you take the weighted average, and if you obtain an average that is close to 7, that tells you that the most prevalent isotope is lithium-7, because the weighted average is very close to 7. So that tells you there is a lot more lithium-7 than there is lithium-6 in nature. And you can do the same thinking with carbon. Carbon has 3 naturally occurring isotopes, carbon-12, carbon-13, and carbon-14. And the weighted average is very close to carbon-12, because it's 12.01 atomic mass unit. So that tells you carbon-12 is the most prevalent isotope for carbon. And for oxygen, the most prevalent is oxygen-16. Fluorine has only 1 naturally occurring isotope. Sulfur has 4, and sulfur 32, 33, 34, 36, but the most prevalent is sulfur 32, etc. So this gives this weighted average that is listed on the periodic table as the atomic mass, you know, gives you an idea of what is the most prevalent isotope for that element. So using the periodic table, fill in the atomic mass for each element. So calcium symbol Ca is found on the left side of the periodic table, and its atomic mass is 40.08 atomic mass unit. Aluminum, under the staircase towards the right side of the periodic table, aluminum 26.98 atomic mass unit. Lead, the symbol for lead is Pb, slightly below aluminum, has an atomic mass of 207.2 atomic mass unit. Barium, on the left side of the periodic table with symbol Ba, atomic mass 137.3 atomic mass unit. Iron, symbol Fe, in the middle of the periodic table on the top, and its atomic mass is 55.85 atomic mass unit. So we will go through how to calculate the atomic mass of an element given the information necessary to get it. And to calculate the atomic mass of an element, you will need to know the percent abundance of each isotope and the atomic mass of each isotope for that element. So you need all of that information to do it. So this would be provided in a text problem. And then to calculate the atomic mass of the element, if the element, for example, has only 2 isotopes, so it will be the contribution of isotope 1 plus the contribution of isotope 2 that you add together to obtain the atomic mass of the element. Be careful, it's not a regular average calculation. You need to take into account the percent abundance. So the contribution of the isotope 1 to the mass is equal to the mass of the isotope 1 times the percent abundance of the isotope 1 divided by 100. And then the contribution of isotope 2, it's the same as a mass of the isotope 2 times the percent abundance of isotope 2 divided by 100. Then you add those two contributions and you obtain the atomic mass of the element. So there is a formula that is provided in the reference packet to you know, remind you how to calculate atomic mass. The best is to go through an example, and we will use chlorine. Chlorine has 2 isotopes. Given the abundance and the mass of these isotopes, calculate the atomic mass of chlorine. So you're given the isotope name on the left, the mass in the middle in atomic mass unit, and then the isotopic abundance given both in percentage and in ratio. So we will calculate the contribution of each isotope. So you multiply the mass of the isotope chlorine 35, so 34.97 atomic mass unit, times its percent abundance, which is 75.78, divided by 100, right? It's a percentage. So when you use percentage, you divide by 100, which is like multiplying by the ratio. And you need to calculate the intermediate answer. It is necessary to show your work when you do this and show the intermediate answer with all the digits maybe not all, but enough digits after the decimal point. Then you take the contribution of chlorine 37, which is taking the mass of chlorine 37, so 36.98 AMU times the isotopic abundance of chlorine 37, which is 24.22 divided by 100. Then you calculate that intermediate answer and write it down with enough decimals. So before you add them to obtain the atomic mass of chlorine, you need to pay attention to significant figures and decimal places, right? And here we have first multiplication and divisions. And we need to evaluate where we would round if we were to round the intermediate answers, but we do not round intermediate answers. It is important here to keep as many digits after the decimal point to not have rounding errors at the end. So because the rule for multiplication and division is to keep the least number of significant figures, here, the mass has 4 sig figs. The percentage has also 4 sig figs. The 100 is an exact number. This is not limiting. So then you need to keep 4 sig figs for the intermediate answer if you were to round. So you keep the 2, the 6, the 0.5, and then the first 0 after the 5. So that's why the 0 here is underlined to say I would stop there if I were to round, and that would mean 4 sig figs here. You do the same thing with chlorine 37. Chlorine 37 also has 4 sig figs in the mass, 4 sig figs in the percentage, 100 is exact. So this time you keep the 8.9, 5, and 4. That's 4 sig figs. Now, when we add them, the rule changes. It's not anymore the least number of sig figs. Instead, it is the least number of decimal places. So it's good to align your intermediate answers according to the decimal point. And here you see that the least number of decimal places would be from chlorine 35 contribution, because you see only 2 decimal places. For 4 sig figs, it translates into 2 decimal places. And for chlorine 7, 4 sig figs translate into 3 decimal places, which is more. So the least number is 2 decimal places. So when you add those 2 contributions, you will keep 2 decimal places. And that's why the atomic mass of chlorine is 35.45 atomic mass unit. So let's go through other examples using the isotope of magnesium. Magnesium has 3 naturally occurring isotopes. Magnesium 24, magnesium 25, and magnesium 26. As you can see, number of protons is the same, number of electrons is the same, and it's the number of neutrons that changes, and that changes also the mass number. So we are given the mass of each isotope and the percent abundance. So given this information, calculate the atomic mass of magnesium. So here we will only use the last 2 rows of that table. And so put together, you will take the atomic mass of magnesium 24, which was 23.99 times its percent abundance, 78.70 divided by 100. here we have 4 sig figs in the mass, 4 sig figs in the percent abundance, because the 0 here is significant. We see the decimal point, so that makes the 0 significant. 100 is exact, it's not limiting. 4 sig figs translate here into 2 decimal places. And remember, we do not round intermediate answers. You want at least 1 more decimal than where you would stop. The contribution of magnesium 25 is 24.99 atomic mass unit times 10.13 divided by 100. Again, we have 4 sig figs in the mass and the percentage. And 4 sig figs this time will translate into 3 decimals. Magnesium 26, again, 4 sig figs in the mass and in the percentage. And because the contribution is small, that translates into 3 decimal places. So when you add them together, now that you add, you need to keep the least number of decimal places. And the least number of decimal places is 2 from the magnesium 24. You add those contributions together and you obtain 24.31 when you round to 2 decimal places. I think the most difficult in these calculations is actually paying attention to significant figures and then decimal places, following the type of operations. So what is good about real elements is that you can look at the answer on the periodic table and verify your work this way. Magnesium, if you look at the periodic table, magnesium is atomic number 12, and you find in the periodic table that indeed its atomic mass is 24.31 atomic mass unit. So this is the way to verify your answer. But be careful, a lot of exercises are using fictive elements and invent fictive numbers, so you cannot verify your answer. So this is to make sure you make the effort to learn how to do these calculations, because you need to be able to do them. So let's go through one more example of atomic mass calculation, and we will use gallium. Gallium is an element found in lasers used in compact disc players. Gallium is a metal. So a sample of gallium is composed of 60.11% of gallium-69, and you're given the atomic mass for that isotope. And it's made of 39.89% of gallium-71, and you're provided the atomic mass for that isotope. So given the abundance and the mass of these isotopes, calculate the atomic mass of gallium. Again, you need to practice this on your own before you watch the answer. So here, if we set up the problem, it looks like this. The contribution of gallium-69, you will use its atomic mass, 68.93 atomic mass unit, times the percent abundance, 60.11 divided by 100. And you write the as much as you can of the intermediate answer. Both the mass and the percentage have 4 sig figs, so you keep 4 sig figs for the intermediate answer without rounding. Remember, do not round intermediate answers. Gallium-71, so its contribution is 28.289. That's also would be rounded to 4 sig figs if we were to round, because the mass has 4 sig figs and the percentage has 4 sig figs. So we keep for sig figs. And now we are ready to add them together. 41.433 plus 28.289. And when you add, the rule is to keep the least number of decimal places. And in both cases was 2 decimal places. So then you would round the final answer to 69.72 atomic mass unit for gallium. And gallium is a real element below aluminum in the periodic table. And its atomic mass is indeed 69.972 atomic mass unit. And that's the end for section 2.3.